Good morning students, welcome back to another Waidsum Academy video. Today we are going to be learning IGCSE Chemistry Chapter 14, Metals. So in our last chapter, which is 13 and 12, we learned about the periodic table and we've learned about the non-metals, metals and metalloids. Well, in this chapter we're going to learn more. We're going to take a deep dive into metals. And we're going to learn about their chemical properties and physical properties of metals and the uses of popular metals such as copper and aluminium and so on. Let's begin. So there are many questions that people tend to ask when you're studying chemistry. Are very important. They are what gives basic oxides and they help us with, they can act as catalysts. Transition metals can act as catalysts and form colored compounds. So there are questions to what metals are. Now you see in this robot in this picture is a space vehicle and it's called Curiosity. It was designed by NASA to roam on Mars and take images of the surface of Mars. You see, Mars has a very rocky surface, so as a result, the tires used in the older space vehicles got damaged easily. So it was difficult to replace the tires on Mars. So a new type of tire was needed, and the development of nitinol, which is an alloy of nickel and titanium. We'll learn about alloys later in this chapter. So nitinol was created. It was an alloy made of nickel and titanium, and it helped you solve the problem of damaged tires. This alloy has a unique property that helps the tires roll over sharp rocks and become deformed, but they can return to their original shape. So when they roll over sharp rocks, they get deformed, but they turn to their original shape. Thus, the tires will not get damaged easily. So this is why they use nitinol. An alloy is a metal created by two different metals to produce a specific properties needed to create an alloy. So let's move on to section 14.1, which is metals and their properties. So in this diagram, you can see we have metals and non-metals. In the diagram, they show that metals can come in different forms, most being solids. But there are some metals, one metal in liquid form, which is mercury. Mercury is the only metal that is liquid in room temperature. Then in solids, we have many metals such as gold and aluminium. Most of these metals are shiny, lustrous. That means they shine under light. And they are mostly solids, except for mercury, unlike non-metals, which are dull and gas, volatile, liquid, or solid. Non-metals can come in all types of forms, and they are not shiny. For metals, they have high melting and boiling points. However, non-metals have low melting and boiling points, except for carbon and silicon. Silicon is considered a non-metal. And for metals are more ductile. That means they can be shaped into wires and malleable, which means they can be hammered into different shapes without breaking. While non-metals are brittle if they're solid. That means you can shape them into wires or hammer them into different shapes. They will most likely break. And most metals are also sonorous. That means they make a ringing sound when struck. Have you ever hit in a bell? When you hit a bell, bells are made up of metals because metals are sonorous. And when you hit a bell, it makes a ding sound. So this is because metals are sonorous. Metals also have good thermal conductivity and good electrical conductivity, however, non-metals have poor, except for carbon. Poor thermal conductivity, except for carbon, and poor electrical conductivity, except for carbon as well. So carbon in the form of graphite and diamond is have good thermal conductivity and electrical conductivity, but other than that, most non-metals cannot conduct electricity or conduct heat properly. Now, what are the chemical properties of metals? Most metals react with acid, water, and oxygen to give similar products. Example, when metals react with acid, a reactive metal reacts with acid to form salt and hydrogen. We learned this in chapter 12, where we talked about the oxides, acids, and bases. And when reactive metals react with cold water to form metal hydroxide and hydrogen. And that means when you add water to metals, they can form metal hydroxide and hydrogen. But some metals do not react with cold water, but will still react with steam to form a metal oxide and hydrogen. When metals react with oxygen, they form a metal oxide. Here are a few examples. We have magnesium reacts with dilute sulfuric acid to form magnesium sulfate and hydrogen. Zinc reacts with dilute hydrochloric acid to form zinc chloride and hydrogen. Calcium reacts with dilute nitric acid to form calcium nitrate and hydrogen. Now we go to song, where we go to the uses of metals. In this section, we are going to learn about the uses of metals. Metals have many uses. Because of their high melting and boiling points, their ductility and malleability, and good thermal and electrical conductivity, metals are used in almost everything we use in our everyday lives. Now in this section, we're going to learn why. So the uses of metals depend on their properties. Each metal has its unique properties. Some metals, such as copper, have good electrical conductivity and are used to make wires. Others, such as gold and silver, are very shiny and are used to make jewelry. Let us take a closer look at these two metals, aluminium and copper. So what are the uses of aluminium? Pure aluminium reacts with oxygen and air to form a thin layer of aluminium oxide, and because of this, it makes it harder for aluminium to rust or corrode. So this makes it popular in many uses, such as using to create cans and food containers. There are main uses of aluminium: aircraft, overhead electrical cables, and food containers and cans, as I said. Why do we use aluminium to create aircraft? Aluminium is used in the manufacture of aircraft and it has low density. This causes aluminium to be very light. So that means it will be better to make airplanes using aluminium other than other metals which tend to have large density. Aluminium is also a strong metal. It doesn't get damaged very easily. And it does not corrode easily either because of the thin layer of aluminium oxide. Now, aluminium is also used for overhead electrical cables because aluminium has low density and is a good conductor of electricity. And it's also ductile. That means people can change the shape of aluminium to form wires. Now, aluminium is used for food containers and cans as well because it is malleable and it does not corrode easily. Malleable meaning they can hammer the metal into different shapes, and not corroding easily means it won't rust easily. Because when a metal corrodes very easily, it's dangerous to use it to make food containers and cans. But because of the thin layer of aluminium oxide, it doesn't corrode easily, and you can use it to manufacture food containers and cans. Now we move on to copper. Copper is a different metal, and unlike aluminium, copper is very unreactive. So it's an unreactive metal that corrodes slowly. When copper corrodes, a green layer is formed on its surface. The green layer prevents copper from being corroded further. Now, this unique property of copper brings it its own usage for. People use copper to create electrical wires, cookware, and roofing. So why is copper used to form electrical wires? Well, because it's ductile. That means you can easily shape it to form wires, and it's a very good conductor of electricity. How? Because copper is a metal, it has a good conductor. It's a good conductor of electricity. But the thing is, copper is so good at conducting electricity. It's the best used, best is the second best metal used for electricity conduction. So we use copper instead of silver or other metals because it's easier to get and it's very good at conducting electricity. It's also used for cookware because it's a good conductor of heat as well. Silver is actually the metal of the best conductivity when it comes to electricity and heat. But the thing is, silver is harder to get compared to copper. Copper is the second best, so copper tends to become more popular than silver. So copper is also used for roofing as it's very unreactive. If you read the reactivity series, copper is known to be at one of the lowest. And because of this, it's very unreactive, allowing people to use it as roofing as it won't react with the air to form rusting and so on. It corrodes very slowly. So let's move on to alloys and their properties. Now here in this section we'll learn about alloys. What is alloy? An alloy is a mixture of metal with other elements. Because you see, why is alloys used more? You see, pure metals, tend to be actually quite soft. They can be hard, but not hard enough for us to use it to create big manufacturers such as ships and cars and trains. Because all these vehicles and buildings and so on use lots of metals, but pure metal isn't strong enough. So to solve this, people created alloys. An alloy is a mixture of a metal mixed with other elements. That means you take a metal and mix it in with other elements, both with metals and non-metals. This allows alloy to become stronger, 10 times stronger than its original element. Now, why do we use metals are often used as alloys? Why? Because it makes metals stronger. Example, brass. Brass is an alloy of copper and zinc. That means when you mix in copper and zinc, you form brass. It's used because it's harder and stronger than pure copper and zinc. And another reason why people use alloys is to improve the appearance of metals. Pewter, which is an alloy of tin, antimony, and copper. It is used to make ornaments because it looks more beautiful than pure tin. It's also used to lower the melting point of metals. Some metals have large melting points, and this requires large temperatures when you want to melt the metals to react. So when you want to take a metal to melt it, it will be expensive because it requires large amount of high temperatures. So instead of spending too much money to buy heat, you could use alloys. Alloys lower the melting point of metals, such as solder. Solder is an alloy of tin and lead and has a lower melting point than most metals. It can be used to join electronic parts to circuit boards. To make metals more resistant to corrosion. Corrosion and rusting is a big issue with metals because many famous pure metals like iron corrode and rust very easily because it reacts with the oxygen in the air and sometimes with water as well. So humans also created alloys to help it rust slower. Copper nickel is an alloy of copper and nickel and is used in coins because it does not corrode easily. Now we go to examples of alloys and their composition, properties, and uses. We have brass. Brass is 70% copper and 30% zinc. It's resistant to corrosion and is an attractive yellow color like gold. So because of that, you can use it for decorative items, musical instruments, and coins. Stainless steel is 73% iron, 18% chromium, 8% nickel, and 1% carbon. Stainless steel is resistant to corrosion. So because of this, it's used in cutlery and utensils and medical instruments. These these type of uses need metals that cannot corrode very easily, resistant to corrosion as well. So it's pipes in chemical industries. So all these uses allow stainless steel to be very useful because of its unique properties. Then we have solder. Solder is 50% lead and 50% tin. It has a low melting point and it's used for joining metal objects because of its low melting point. We have pewter, which is 95% tin, 3.5% antimony, and 1.5% copper. It's bright, shiny like color like silver, and it's used for decorative ornaments. Now we go to how is the structure of an alloy different from that of pure metal. You see, metals atoms are the same size. In a pure metal, the structure of a pure metal, here each ball represents a metal atom, and all of these are the same size. But because of this structure, this formation, when you add force when force is applied to pure metal, it gets the layers of atoms slide over one another. So thus pure metals become soft because it's easier to cut or slide or bend pure metals. Pure metals because they're all of the same size. Now, but when you mix in a metal with a different atom, atoms comes in different sizes. So when you mix in an atom of another element with a metal atom, you get to have a stronger and harder solid. Because when force is applied, the shape of the atoms of different sizes cannot slide over each other. So when force is applied, it cannot bend or get shaped easily. So thus, alloy is stronger and harder than pure metal. Now we go to 14.4, which is the reactivity series. Here we are going to learn about the reactivity series, how reactive each metal is. So let's move on to what is the order of reactivity metals. You see, why do coins made of zinc look dull after some time, while gold coins remain bright and shiny for years? This is because zinc reacts with the air faster than gold does. In other words, zinc is more reactive than gold. A metal that reacts faster or moves violently is said to be more reactive than the other metal. So it is useful to arrange metals according to how reactive they are. Thus, scientists have come up with a list, what we call the reactivity series. In the reactivity series, metals are arranged from the most reactive to the least reactive. You can see in this reactivity series, we have the most reactive being at the highest and the least reactive being at the lowest. Potassium is considered one of the most reactive metals. Then we have go on down to sodium and calcium, magnesium, aluminium. And as we go down, the lower we get, the less reactive each metal becomes. So note that carbon and hydrogen are also included in the series, even though they are not metals. The reason is because of their inclusion will be explained later in this chapter. So the order of reactivity metals can be determined. The order of reactivity metals can be determined by the reactions of metal with cold water, steam, and dilute hydrochloric acid. When you react metals with cold water and steam, some metals, such as potassium and magnesium, react with cold water. So more reactive metals react violently with cold water. Some metals, such as zinc and iron, do not react with cold water, but react with steam. Some more reactive metals react more violently with steam. There in this diagram uh, shows this shows the apparatus for the reaction of a metal with steam. The metal is strongly heated, and a glass soaked with water is also heated to generate a flow of steam over the hot metal. Here you can see the hot metal. The metal is being heated with a Bunsen burner or any source of heat, and a glass wool soaked in water is put at the side. From there, the metal reacts with steam. This is water and hydrogen gas. When the water is the hot water, the steam flows through this rod, and as it does so, the metal reacts with the steam. And depending on the reactivity, depending on the metal's reactiveness, the metal can react differently. Each metal can react differently to the steam. Now, the table here shows the observation and simple equations for the reaction of some metals with cold water and steam. We have potassium, sodium, calcium, and magnesium. Now, potassium reacts very violently to form potassium hydroxide and hydrogen gas. Enough heat is produced to cause hydrogen gas to cause fire and explode. Some sodium reacts violently to form sodium hydroxide and hydrogen gas. Hydrogen gas may catch fire and explode, as you can see in the formula. Calcium reacts readily to form calcium hydroxide and hydrogen gas. As we go lower down the reactivity series, you'll notice that if the reaction and the observation is slowly decreasing, the top three in the reactivity series react explosively. This reaction should be carried out in a school laboratory. But other than that, as we go down, the other metals that are not in the top three do not react as explosively as the more reactive metals. So this metal reacts very slowly with cold water to form magnesium hydroxide and hydrogen gas. A test tube of hydrogen gas is produced only after a few days. So hot magnesium reacts violently with steam to form magnesium oxide, which is a white solid, and hydrogen gas. A bright white glow is produced during the reaction. Now, how about reactions of metals with dilute hydrochloric acid? Many metals react with dilute acids to produce a salt and hydrogen. When a metal reacts with dilute hydrochloric acid, the products are metal chloride and hydrogen gas. The reactions of different metals with dilute hydrochloric acid, no hydrogen gas. The reactions of different metals with dilute hydrochloric acid also indicate how reactive the metals are. A more reactive metal reacts more violently. So here's this table that summarizes some of the metals with dilute hydrochloric acid. Magnesium reacts rapidly to give hydrogen gas. Zinc reacts moderately to fast to give hydrogen gas. Iron reacts slowly to give hydrogen gas, while copper, silver, and gold do not react with hydrochloric acid at all. So when we recall the position of hydrogen in the reactivity series, metals above hydrogen in the reactivity series react with hydrochloric acid to produce hydrogen gas. Based on the reactions of the metal with cold water, steam, and dilute hydrochloric acid, we can place the metals in order of their reactivity. The reactivity series can be used to predict the behavior of a metal from its positions. So, the reactivity series can be used to predict the behavior of metal from its positions in the reactivity series and predict the position of an unfamiliar metal in the reactivity series from a given set of experimental results. Here we have apparatus on reactivity of aluminium. Aluminium is above zinc in the reactivity series, but a strip of aluminium left in the open does not react with water. Aluminium reacts readily with oxygen in the air to form aluminium oxide. This layer is insoluble in water. It prevents aluminium from reacting with water. We've learned that aluminium reacts readily with oxygen in the air to form aluminium oxide. This layer is insoluble in water and it prevents aluminium from reacting with water. So, what is the relationship between the reactivity of metals and their tendency to form ions? In chapter 4, we learned that metals tend to lose electrons from their positive ions. The reactivity of a metal is related to its tendencies to form positive ions. A more reactive metal has a greater tendency to form positive ions compared to less reactive metals. For example, when potassium reacts with water, it loses electrons to form positive potassium ions. So when we have K, which is the symbol for potassium, when it reacts with water, it forms K plus. It forms positive ions plus. It forms positive. Sorry, excuse me now. It forms positive ions because it loses electrons. Magnesium, however, loses electrons less readily compared to potassium. This is why magnesium does not react as violently with water compared to potassium. The reactivity series may be used to explain the displacement of reactions of metals. A more reactive metal can displace a less reactive metal from its salt solution. For example, when the iron fillings are added to aqueous copper 2 sulfate, a copper metal is precipitated from out of the solution as a pink solid when freshly formed, or a red-brown solid. The solution then turns green. We say that iron has been displaced from copper from aqueous copper 2 sulfate. The reaction can be represented by the equation shown. When iron mixes in with copper 2 sulfate, the iron displaces the copper and it becomes iron 2 sulfate plus copper. A more reactive metal forms the positive ions more readily. Since the iron is more reactive than copper, the iron atoms become iron 2 ions and form iron 2 sulfate. The ionic equation is shown here. The iron atoms become iron 2 ions and the copper 2 ions change to copper atoms. On the other hand, if a piece of copper foil is dipped into aqueous iron 2 sulfate, no reaction occurs because copper is less reactive than iron. It has a lower tendency to form ions compared to iron. Thus, it cannot displace the iron from its salt solution. Displacement reactions of metals. If a piece of copper foil is dipped into aqueous iron 2 sulfate, no reaction occurs. Copper is less reactive than iron, so it has a lower tendency to form iron compared to iron. Thus, it cannot displace iron from its salt solution. Now, this table given shows some of the observation from the experiment. Let's investigate 14.8, which is let's investigate 14.8 is not shown in the PowerPoint. But actually, I'll explain to you. They say that in Let's Investigate 14.8, they say they investigate the displacement of metals from their solution by another metal. Now, this table shows the results for that. We can see that a metal higher up in the reactivity series will displace a metal that is lower in the reactivity series to form a salt solution. Let's look. We have magnesium as a metal. It cannot displace magnesium sulfate, but it can displace zinc sulfate, iron 2 sulfate, copper 2 nitrate, and silver nitrate. So you can see, because it's the most reactive metal here in this table, it can displace every single metal except its own metal. Zinc, on the other hand, is the second most reactive metal in this table. It cannot displace magnesium, and it cannot displace zinc either because it's zinc. Why can't it not displace magnesium? Because zinc is less reactive than magnesium. But it can, however, displace iron, copper, and silver to form colored compounds. Iron cannot displace both zinc and magnesium because it's less reactive. Copper cannot displace magnesium, zinc, and iron, and silver cannot displace any of them at all. No change is observed. So displacement reactions of metals. In a metal displacement reaction, the more reactive metal is oxidized while the less reactive metal is reduced. Thus, a displacement reaction is also considered a redox reaction. For example, a redox reaction occurs when magnesium displaces copper from copper to salt solution. The more reactive metal magnesium reduces the copper to ions to copper, and magnesium itself is oxidized to magnesium ions. Now we're going to section 14.5, which is the corrosion of metals. Many metals corrode, and because of this, it's kind of difficult to use metals for our daily usage because it corrodes quite easily. But now we're going to learn how it corrodes and how humans have tried their ways to stop it. Now we go to corrosion of metals. When a metal of iron is exposed to moist air for some time, a red-brown substance slowly forms on the surface of the metal. The substance is called rust, and it has a chemical name called hydrated iron trioxide. Rusting or corrosion of iron is the process that produces rust. It is a slow oxidation of iron to form hydrated iron trioxide, which is known as rust. The equation of rusting is iron plus oxygen plus water gives hydrated iron trioxide. The X in the chemical formula of hydrated trioxide indicates the number of water molecules present in the compound. So, what causes rusting to occur? The presence of both air, which is oxygen, and water are necessary for rusting to occur. The essential conditions for rusting are studied in the experiment of Let's Investigate 14b. The results of the experiment are summarized on the table. So we have the 4 test tubes, and they have different conditions. So test tube A has oil and boiled water and a cleaned nail, while test tube B has cotton wool and anhydrous calcium chloride and a clean nail. Test tube C has just water, and test tube D has aqueous sodium chloride. So for test tube A, water is present while air isn't. Because of the oil, the air is not present, and if you observe after some time, test tube A, the clean nails in test tube A will not occur, rusting will not occur. In test tube B, there is no water present, but there is air. But since there is no water, rusting still does not occur. But for C, there is both water and air. So that means the nails rusting will occur. But for D, instead of water is there, but it's aqueous sodium chloride after a week. So after a week, the nails will rusted very heavily compared to the other test tube because D had aqueous sodium chloride. So both air and water are needed. From this table, we can conclude that both air and water are needed for rusting to occur. The presence of sodium chloride increases the speed of rusting. We can say sodium chloride is acting as a catalyst here. Acidic substances such as sulfur dioxide, carbon dioxide also speed up the rusting process. Thus, iron objects near the sea and in industrial areas corrode more rapidly because of the presence of salt and other pollutants in the air. So how can rusting be prevented? Here are different methods for preventing rusting, which should be memorized and noted down because they will ask me your IGCSE question. There is a common method for large objects for such as cars and ships and bridges, which is painting. Painting is when you paint the metals. Painting is where you paint the big objects, large objects such as cars, ships, and bridges. However, if the paint on the object is scratched, rusting will take place on the painted surface. Then we have oiling/greasing. This is a method used for machinery such as tools and machine parts. The protective layer of oil or grease is added to the machine, and this prevents oxygen to react with the iron. So this is a good method, but the protective layer of oil and grease must be renewed every now and then. Then we have coating with plastic. This method is used for smaller objects such as kitchenware and steel clips. This is also a good method, as it is also you do not need to replace it as commonly as oil and grease. But the issue is if the plastic layer is torn, the iron starts to rust. Then we have sacrificial protection. Sacrificial protection is the protection of iron and steel against rusting by using a more reactive metal such as zinc to coat the entire metal. That means we cover the entire iron with a layer of zinc. This will allow the zinc to react to the oxygen and in the air and water if it gets splashed with water. So why does this happen? Because zinc is a more reactive metal than iron. So the more reactive metal will react more readily with oxygen and water and will corrode instead of iron and steel. This method includes galvanizing or coating with zinc. Zinc acts as a barrier and keeps the iron or steel away from the air, and attaching a more reactive metal such as zinc to iron or steel. And because of this, the zinc is more reactive than metal. Zinc has a higher tendency to form positive ions. Zinc loses electrons in the preferences to the iron and prevent iron from forming iron 3 oxide, which is rust. Therefore, more reactive metals such as magnesium and zinc will corrode instead of iron. As long as the magnesium or zinc is present, iron will not rust. This is called sacrificial protection because the more reactive metal is sacrificed to protect the iron or steel. Now here are the formula. As you can see, iron loses 3 electrons to form iron 3 ions, but zinc can lose 2 electrons to form zinc ion. And since zinc is my mirror board is lagging, please give it a moment. Since zinc is more reactive than iron, zinc has a higher tendency to form positive ions. Zinc loses electrons in the preferences to the iron and prevents iron from forming iron 3 rust. You can see in the formula, zinc can lose 2 electrons to form zinc ions, while iron loses 3. So instead of letting iron to lose 3 electrons, we use zinc to react with the oxygen and water to allow it to react with the oxygen and water to allow it to rust. So the zinc in this scenario sacrifices itself for iron. So iron preventing the iron to rust and to react with the water and oxygen in the air and rust. So this is the end of our Waidsum Academy video. Thank you so much for listening, and I will see you all in the next class. Goodbye.